So I record, I continue. There is also reason I told you, right? I record first part and then stop record and I second record because hopefully if there is error, we don't lose all recording lah. Hopefully we manage to recover one of the part lah. Okay, so if we direct record everything, if something happen, all of it will go now. So that's why I do like this we relax and then we take second part of recording. Okay, so okay, now is AM single sideband suppressed carrier. So this one select. Okay, I check on the BP Lati book. This one is a signal book, signal and system book. Okay, maybe last time I don't know if you're okay. I teach some of you signal system, but some of you I didn't teach, right? I didn't taught you last time for signal system. So signal system, we use this book BP Lati. But for my class last time, I already explained to them it's not compulsory to buy the book because the book doesn't really cover the entire syllabus for the BP Lati book. So, but the BP Lati book also covers some portion of this communication principle. So, but when I check 176, okay, I check 176 of Lati. It's actually exercise. It's exercise page. So I'm not sure whether it's the correct page or not. Okay, filtering method. Okay, because it's 176 is the exercise. It's not about filtering method. So if you want to learn more, maybe you can see from the BP Lati book. If you have soft copy, I'm not sure. You can search pretty much many things online right now, right? Even though, including the pirate book, okay. But I'm not sure where to get it. But you guys can get it if you can get it online, or you can buy it. Okay, depends on whatever method. But this one is the information there. But I don't really see which pages actually. I opened 176. I didn't find this. Okay, maybe I didn't find by scan through. I don't really read by words. If I read by words, we waste our lecture time. Okay, so single sideband suppressed carrier. So we only submit one band, which is upper sideband or lower sideband, and we did not submit carrier. So in the three components, okay, three component which is upper sideband, carrier, lower sideband, carrier, and upper sideband, we only transmit one of the sideband without the carrier. Okay, so only one. So can be realized by in two steps actually. Generate the first double sideband suppressed carrier. You see this one. So you generate first the full sideband, means having two sideband without the carrier. And after that, you just use filter. So it's pretty much direct lah. So VMT cos omega CT is balanced modulator. If you see this one, this method, okay, try to compare with the previous figure, okay, you see the relation actually. If you refer from the previous figure. So the question pretty much asks you how to generate this signal. What is the circuit direct method? So you should know because it's pretty much related. For example, for double sideband full carrier, okay, double sideband full carrier looks like this, but we have a amplifier, okay, and then we add it back in order to have double sideband full carrier. For the double sideband suppressed carrier, so this is the circuit. Double sideband suppressed carrier. For the single sideband suppressed carrier, you just need to add bandpass filter. Then you have VSSB SEU. Pretty much similar, right? So you understand one circuit, then you will understand, you know how to create another kind of circuit because this is just extension or modify. The circuit will not be totally different. Okay, for the direct lah. Okay, so bandpass filter is tuned circuit that is very selective whether we will choose lower sideband or upper sideband. So that's why we use bandpass filter because you only transmit one of them. Okay, so not important which sideband will be selected because both sideband contain the same information. Like I told you, both single sideband have the same amount of information. So why need to be transmit both? where actually it contains the duplicated informations. Okay, so we can just submit either upper sideband or lower sidebands. Okay, so this is pretty much the another method. We can say indirect method lah. So you can compare this method. You can compare this with double sideband sparse carrier generation. Okay, you can see you try to make difference. Okay, you try to differentiate what is the difference between single sideband suppressed carrier indirect method with double sideband suppressed carrier indirect method. Okay, what is the difference? Okay, you can see in the single sideband suppressed carrier we have what? We have 90-degree frequency shift here. So if initially in the double sideband suppressed carrier is half VMT and this one is negative VMT, then polarity cancel out our carrier component, leaving out only double sideband without the full carrier. In the single sideband suppressed carrier, however, we still using VM m cos omega mt as our input. However, one of the inputs we have to input, one of the input we take directly, and second we introduce 90-degree frequency shift. So you know, right, as you learn from single system and trigonometry, when we introduce phase shift, it will become the next, whether it is sin or it's cos. So this one we introduce phase shift of pi over 2 to cos, so that's why we have sine components. Okay, then at the balance modulator, it just proceed as it is here for this root. However, for this root, it also shifted. Okay, it's also shifted the carrier component. Okay, so you have sin omega CT. So the below part you have full sin m sin CT. This one is cos m cos CT. Then it is just a mixer, double. So you're going to have single sideband suppressed carrier. Okay, so this one cos omega m cos omega c sin omega m plus sin omega CT. So you refer okay, you refer to your appendix, right? You refer to your appendix. Okay, this one is cos A cos B plus sin A sin B. Okay, cos B sin A sin B. Yeah. Okay, so you end up will have cos plus minus xy. Okay, depends on which cos lah. Okay. This one is pretty much the difference. Okay, with the double sideband suppressed carrier, you have 90-degree phase shift on both of the carrier component and the modulating component. So you need to know the difference if the question asks you, or if the question asks you how to generate it. Okay. Of course, the main part actually you need to understand double sideband full carrier, how we produce it, because double sideband full carrier, double sideband suppressed carrier, single sideband suppressed carrier, all of it will take the basic from double sideband full carrier. Okay, the circuit is almost the same, you just add some difference. Okay, some addition. For example, this one you introduce 90 phase frequency shift to both input and to carrier. Okay, in contrary with a double sideband suppressed carrier. You see, almost the same. Double sideband suppressed carrier with single sideband suppressed carrier. For single sideband suppressed carrier, you just add 90-degree frequency shift on the input side here, and you introduce 90-degree phase shift to your carrier components. Okay, for this full AM modulator 2. This one is full AM modulator 1. Okay, balance modulator pun lebih kurang. Okay, so the outputs of this one is mathematic. Okay, we already okay, this one is mathematics, so cancel out. So you only submit lower sideband. Okay, lower sideband. So this one is you can expand this cos omega m, cos omega ct. So what actually resulted this? Okay, this is trigonometry. Trigonometry. So you can test yourself, what if we want to submit upper sideband? How is it? What if we want to submit upper sideband? Okay, so upper sideband, of course, the end product should be em cos omega c plus omega m. But what is it different? What is it different? What different that what is the difference with this and the previous operation in order to produce upper sideband? Okay, try this at home. How to produce upper sideband? Okay, pretty much is the same lah. Okay, this one is what we call is vertical sidebands. We transmit, for example, if you want to transmit upper sideband, yes, we transmit the totality of upper sideband with a portion of lower sideband, or we want to submit the totality of lower sideband with a portion of upper sideband, something like that lah. So in this case, if for this figure, we want to transmit upper sideband. Okay, yes, we transmit the totality of upper sideband with a portion of lower sideband. So that's why we submit a portion of this, and this one is filtered out lah. Okay, so you see VST is our signal, input signal, and we have 2 cos omega ct, which is our carrier. Then you have double sideband suppressed carrier. Then if we go to VSP filter, VSP filter means, of course, the filter, it will filter this lah. Okay, so we only pass through this, and the rest are being filtered out. Okay, we only transmit this. So then we have vertical sideband. Okay, laju pula saya ni, tapi because this is theoretical, if you don't understand, you let me know. Okay, so this is the next one is the demodulation. Okay, so when we have a transmitter, so we transmit our modulation signal, okay, VM, okay, amplitude modulation signal, whether it is a double sideband full carrier, double sideband suppressed carrier, what else? Single sideband suppressed carrier, or vertical sideband suppressed carrier. There is 5 lah actually, right? But the main is like 4 lah. This is all modulated signals. Okay. However, when we want to transmit, when the reason we transmit with modulation signal, so that our signal can be suit to the communication channel, and also for travel over long distance, and also many things also, like I explained to you last time, right? Antenna, if we don't modulate it, the antenna will be big, right? So many things you can actually refer to the previous lecture, recap from the lecture slide, whatever. Okay, if you don't understand, you can go to me. And so whatever the modulated signal, our intention is that for it to be transmitted to receiver. Okay, so sooner or later the receiver will have it. Okay, so this is modulated signal being submit. So when we receive back to our receiver, okay, in which form that we receive, whether it is a upper sideband, whether it's a double sideband full carrier, double sideband suppressed carrier, single sideband suppressed carrier, or vertical sideband suppressed carrier, at the receiver part, we need to demodulate. Okay, we need to demodulate it back. Okay, in order for us to extract the original signal. Okay, for example, if the original signal, you want to submit this information signal, hopefully, okay, after demodulation, filtering, whatever, removing the noise, hopefully we're able to receive the original signal again, the original information. So usually, of course, for example, normally maybe initially this one is higher, for example 10, for example only, for example 10 volt, okay, of the information signal. Normally we not receive 10 volt okay, or normally it will be weak signal because it travel long distance, disturbed with noise and everything. It will have lower in amplitude. Okay, but at least the information is the same, or most likely almost the same as the information signal lah. Sometimes it's not 100% lah, because it's after disturb binary whatever. And when we receive, it's normally weak in amplitude, but it's okay. When it's weak in amplitude, we can put amplifier again to amplify it again, but at least the information is the same, okay, or most likely similar lah, okay. With the E10, what we transmit here, we hopefully that we receive the same thing back lah. That is the goal of the communication transmission. Okay, so the process of recovering the modulating signal or the original message signal, this is what called as the demodulation. Okay, so demodulation is performed by demodulation circuits, okay, also known as detector circuits. Okay, so the other, for example, names are many names. We have demodulation. Okay, if we tell you detector circuit, what is detector circuit? Detector circuit is demodulation circuit. Okay, don't think that, for example, oh, we don't learn about detector circuit, we learn demodulation, but it's actually the same thing. Okay, demodulation and detector circuits are the same things. Okay, the same person, different name, that's all. So okay, this is the transmitter and this is the receiver. Okay, so we have the modulation methods, whether it's AM or FM. Okay, but so far we learn FM, so that's why we cover FM later. FM is the next chapter frequency modulations. Okay, so the next we have the simple and most economic detector for AM signal is the envelope detector. Okay, the simplest and most economic is the envelope detector. You know, right? When we transmit, this is our modulated signal, right? So this is the envelope lah. Okay, the envelope equation is EC plus VM. Okay, so this is our envelope equation. Okay, and this our envelope, and this is our cos omega CT lah. Okay, so this is our envelope. Okay, so the simple and most economic detector for AM signal is envelope detector. Okay, the main reason why AM is more popular than DSP-SC or SSB-SC. Okay, so this is the main reason. The main reason why full AM, double sideband, full carrier is more popular than double sideband suppressed carrier and double sideband and single sideband suppressed carrier. Okay, so in the detection parts, okay, even though double sideband, okay, I hope you can relate the advantage, disadvantage, the weakness, the strength, the pro and cons. For example, double sideband full carrier, even though the power is wasting power. Why? Because for example, we transmit the carrier which doesn't have the information, and we submit also both version of sideband which contain the same information. Yes, at the generating it is a bit waste, a bit disadvantage. However, in the detection parts for AM signal, for full AM, double sideband, full carrier, okay, in terms of detection, it is the simple and most economical. So that is why full AM is more popular than DSP. You need to relate okay. Why sometimes we still why you still want to use double sideband full carrier? It's wasting in generating whatever. But you see at the one of the advantages on the demodulation part, on the receiving parts. Okay, because in order to retrieve back the signal, it is more simple economic using full AM. Okay. So envelope detector also we have a different name. Okay, we have a rectifier detector or diode detector. Why we use? Because we have diodes. As you learn from digital electronic device, diode is also a rectifier. What does it mean by rectifier? We actually allow, we change this AC to DC, right? Sorry, not AC to DC. We change it to For example, if you have full signal here, rectifier, if we pass through, we only have one side of polarity. Okay, this one, for example, lah. Okay, so this is the diodes. Okay, diodes only allow the position, the current flow in one direction only. You see here. So if we have different, it is not being considered lah. So we only have the polarity of this one or this one. Depends. Depends on the how the circuit is arranged. Okay, but not both. Depends also. This one is half wave, half rectified, and you have full rectified. Okay, I think you know this, right? This is pretty much electronic device and also signal and system. Okay, so you see, you already learn okay, many names. Okay, you see, you go to previous. Demodulation circuit is also known as detector circuits. Okay, in the full AM detector circuit, how they perform it, they're using envelope detector. Envelope detector, the other name of the envelope detector, also known as rectifier detector or diode detector, because we are using diodes here. Okay, so it is cost efficient, simple implementation, no need to generate local carrier. Okay, later perhaps you will see a local carrier is being used or not. You can see later on. Okay, so the original signal is located at the envelope of the modulated signal. The envelope lah. Just now, right? I show you where is the envelope. Okay, so this is our signal. Okay, this is our signal, and this is your the diode, and this is your envelope detector circuit. Okay, so this entire, not the diodes. Okay, this is your envelope detector circuit. So you have a low pass filter. Okay, so this is RC. Okay, AM modulated. Okay, let me see from which page. Page 54 of your module. 53. 53. Okay, page 53, 54, and 55. Is how we do the envelope detector lah. Okay, envelope detector. Okay, so hopefully you spend some time to read how to about the envelope detector 2.8.1. Okay, because I think many important information there. And also double sideband full carrier is just like the basic for all things, something like that lah. Okay, the rest is just modification. The rest, for example, extend. For example, double sideband suppressed carrier, single sideband suppressed carrier, vertical sideband suppressed carrier, they are all actually more or less depend on your understanding in the double sideband full carrier, whether generation, modulation, generation or modulation, or receiving or demodulation. Okay, so you need to understand the main part first. Okay. Okay, so I think Zianwai have shared in the telegram. So we turn to page 53. Okay, page 53, 2.8.1. Okay, you see here paragraph 2, envelope detector circuit comprised of diode rectifier, low pass filter, okay, which is this. Okay, see the books, low pass filter. Okay, with time constant RC. Okay, this is time constant RC. Tau equals to RC. Okay, tau equals to RC, which is your time constant RC, followed by DC block. Okay, followed by DC block. Second representation is shown in figure 2.19, okay, which is the one that we show in the slide right now lah. Okay, so RC is chosen so that the output signal from the rectifier diode is according to the envelope modulated signal and not the fast changing carriers. So the way we choose our RC also there is different. If you choose RC too small, what is the difference? If you choose RC too large, is what is the difference? So the difference is shown in figure 2.20 of page 54, okay, of the module. Okay, if you have RC is too small, you can see that it is have more sharp going down. Okay, so sharp going down. Okay, if you have RC too large, it will have slow turn down. Okay, you can see the shape lah, which one actually more contribute to the shape of our signal lah. Okay, so you cannot have RC that is too small, otherwise dia macam bergerigi, look like too many ripple lah. And RC too large, you will have like white ripple lah, something like that lah. Okay, okay, so go back to page 53. Okay, page 53. Because the slide doesn't really have much information, right? Okay, we can okay, the slide is here, but never mind. It's almost the same as what I explained lah. Okay, ripple, whatever. Okay, so look at paragraph 3, page 53. The operation of envelope detector are as follows. During the positive half cycle of the input signal, the diode is in reverse bias. Okay, so if you see, okay, if you see now from the slide, you see from the slide. So for example, for the positive half, half cycle, during the positive half cycle of the position, the diode is in reverse bias while the capacitor C is in low pass filter, which charge up rapidly to peak value of the input signal when the voltage. Okay, you know that.
Maybe the book is typo, I think.
It's actually during the is forward bias, right?
Right. Yeah.
Yes,
it's forward.
Forward bias. Macam pelik je. Okay, during the positive cycle, if you see during the positive cycle, you have positive here. Okay, means okay. The first positive, this one. Okay, the first half. So when this is positive, means it is forward bias, means the signal pass through. Okay, and then we have, for example, the next one is negative. Negative. When the negative, it is reverse bias. Okay, so typo, betul lah typo. Patut saya macam pelik. So this one, the operations of the envelope detector are as follow. Please refer to the book. During the positive half cycle of the position, the diode is forward bias. Okay, forward bias. So then it goes to here lah. Okay, it goes to here. It pass through. What happened to the negative cycle? The negative cycle will not pass through. Means pretty much we only allow a portion of the positive cycle to pass through. Okay, here lah. It here. Okay. After the diodes. Okay. And then the capacitor will charge. This capacitor actually charge according to your RC. Okay, tau equals to RC. While the capacitor in the loop will charge up rapidly. Okay. Okay. So we go to the next slides. Okay. The capacitor will. So there is different. The capacitor will slowly be discharging through the resistor R, the LPF, until the next positive half cycle. Okay, so during the reverse bias, okay, during the reverse bias, it is discharging it is discharging until the next it will be charging again okay. charging again in the next forward bias circle. Okay, so the capacitor will slowly be discharging through the resistor R, the LPF, until the next positive half cycle. So when the next positive half cycle happen, it is charging. Okay. The capacitor will slowly be charging through the resistor R until the next positive half cycle. Yes. So the capacitor actually charging and discharging, right? You know, right? The capacitor and also like the inductor, they are both storing energy. For the capacitor, it store in terms of charge, and the inductor is in terms of magnetic. Okay, so the discharge rate, okay, if you look into the slides, this one is I think we will understand better if we do exercise. Okay. So the discharge rate now, from the first until now is quite like a theory. Okay, so the discharge rate of voltage drop depends on the time, tau equals to RC. Okay, just now when in the previous slide when I say tau equals to RC is not located in this slide, but I know it's tau equals to RC, but it's actually in the next slide. Okay, so we cannot have RC that is too large, we cannot have RC is too small. Okay, because if we have RC is too large, okay, you see that your ripple, okay, the voltage drop is too slow, causes diagonal keep clipping, okay, where the part of the input peak voltage cannot be detected at the output. Okay, refer to figure for this one. Okay, so it will be like, okay, so if it's too small, then you have a lot of too many ripple. Okay, so you actually need to have in between of them. Cannot have too small or cannot have too large. So if RC is too small, the output voltage from capacitor will contain many ripple and desired message will be distorted. Okay. If you have RC too large, you will have diagonal clipping, where part of the input peak voltage cannot be detected at the output. I think clipping you learn right from the digital electronics. Clipping. Clipping. You learn this clipping in the not digital electronic device. Clipping. Not sure, electronic device or electronic circuit and system. But I believe in electronic device, the clipping. Okay. So actually pretty much related. Whatever you learn, it's not always. So when you learn, remember that you don't don't want to remember it at all, because you think like, okay, no need to remember because uh, need to remember maybe because you're not going to relearn it again, you're not going to take the subject again. No, sometimes it is taken to the next subject. Like this. Okay, so this one is the envelope detector circuit. Then why in the final exam or in the test, do they because I cannot check the test right now, do they have this detection circuit or not? Do they, in the test one day I shared both tests, do they have or not? Because sometimes it's better to do exercise.
Let me check first.
Because it's difficult for the student. I think no. Macam tak ada.
Oh yeah, no, yeah, okay. Got for the test one, yeah, it got the diagram for the one for the circuit, including the diode and then the LPF and also the second capacitor and second resistor.
This one, right? It's in the past test, is it?
Yes.
Okay, so you guys can do first. I don't know the question, but I will refer to e-learning tonight. Please do the exercise on the detection, because detection, and because we discussed anti-detection today. So please do the exercise I know it's because now it's just theory. Okay, now it's just theory. Please do the exercise until the detection circuits, and we will try to discuss it tomorrow, okay. Quite boring today. Okay, so try to do the exercise, okay. I will see the question later on, okay, because we have touched for the chapter 2 until we have done on the exercise of the double sideband, full carrier, suppress, single sideband, suppress carrier, and so on. But we didn't yet cover. We didn't do yet exercise on the generation. Starting from direct method, indirect method, because we just did cover today. So if this generation and detection is covered in the test that I shared to you guys, two set, please do it. Don't wait for me. Just do it, because sometimes maybe I say, okay, we discuss. Okay, high chance we will discuss tomorrow. Okay, so please do it first. Banyak ke soalan dia, Zenhua? Is it many question or only one test one actually cover the general?
For the past test that doctor already said, only the third question covering the detection of the signal.
Mutation. Okay.
Yeah.
Only that.
Question 2 is about the generation, and question 1 is about the noise factor, noise figure, something like that.
But generation we have done in class or not? Not yet.
And not yet.
Okay, so try to do it. Both at e-learning, is it? Both this already at e-learning or what?
Let's see.
Hmm.
In the e-learning.
Both both at e-learning. Okay. So you guys can do first. I tomorrow, because sorry, I am so sorry, because this is our schedule that academic office has arranged. Today is your class. Tomorrow is also your class. I actually prefer today is the class, and the class will be the day after tomorrow, which mean which is Tuesday. But it's okay. I know the challenge. It's not easy to arrange schedule for many class for hundreds of students. So we just try to cope lah. But that's why you need to do the homework today, so that we can discuss tomorrow. We cannot wait for the next week, because next week is already like next week, right? So we try to cover until when. Okay, you do exercise generation and detection in the test that I have shared, past test. You do it tonight. Whether you make it wrong or not, it's okay. You do it first, okay? Because right now we only discuss on the theory and only theory, so we cannot know whether you understand or not. Okay, so envelope detector to overcome those effects, whether RC is too small or RC is too low, so you need to use this low lah. It's kind of like a rule lah. Okay, RC greater less or equals to 1 or equal 1 minus m square root over m omega m, and is almost similar to 1 over omega m. Okay, I'm not sure in the appendix is it being shared, this rule. Mana the appendix? Where is the appendix? It is not shared in the appendix. So it is not shared. So let's say if you it is not shared. So let's say if you're not able to you're not able to memorize this 100%, at least you know RC is almost equals to 1 over omega m. Okay, because it is not in the appendix. Okay, so this is, I think, another one equation. Maybe I'm not sure whether it means that this is another equation that maybe it is important, maybe I'm not sure, maybe it is important, but it is not in the appendix. I don't know whether it's important or not, because we don't know your final what's gonna be, right? But at least you know this one is not in the appendix. RC almost equals to 1 over omega m. Okay, if you are unable to memorize this, at least you know this one. Okay, so modulation index and omega m is the radiant frequency of the message signal. I think you know already this one already, right? This is 2 pi fm lah. Okay, so this is the illustration. So this is your modulated signal that you receive. Okay, whether it is double sideband, no, this one is totally double sideband, full carrier. Okay, full AM. Okay, this is the advantage because envelope detector is being applied at at full AM, double sideband, full carrier. Then it passed through the diodes. Okay, when it passed through the diodes, we only take a portions of the cycles, means not all, because this is half wave rectify, not full wave rectify, right? So we only take the positive cycles. Okay, it's here. So you should know what happened. Okay, all of you, you should know what happened. For example, after this, after diode, what happened? After this, what happened? After this, what happened? But you need to understand. Don't memorize. Okay, you need to understand, because when you understand, you don't really need to memorize. Okay, so this one is what you understand from the electronic device for the diodes. Okay, it change to it's rectified means half portions of the positive cycle or negative portion of the negative cycle, or full rectified. Okay, but this one obviously is just half. So we rectify, we only take the positive portions, but still we have this one. You see inside here, this one is our just now this one. Okay, so then after the low pass filter, okay, after the low pass filter, we actually remove what happened when the low pass filter, we remove what? Can anyone answer me? Low pass filter is removing what? Anyone? Daniel, Hanisa. Actually, low pass filter is removing what? No, actually being removed by this low pass filter. Yes, it's removing high frequency lah. So you only have the frequency that is almost similar to your information signals. However, it's not exactly as your information signal yet. Okay, because we still have DC components. Okay, and then here is where we remove the DC component. As you learn from your signal and system, okay, signal and system, this is like a signal of repeat periodic signal with a DC shift, with amplitude shifting. So we need to add another DC component blocker for us to remove the DC part. Okay, so when we remove the DC part, so we bring down, for example, for this case, we bring down the signals because it has been shifted upwards by a DC level. So this is where when we pass through the DC component blocker, you get the original signals. Okay, the original signal. Okay, if you refer, please refer to page 55. Okay, please refer to page 55. There is a page 55 of module. There is mentioned KT, okay, where KT is mathematical representation of the diode switching function. Okay, so KT normally is given. If it's in the question, it is given. You don't need to find what is KT. No, but if it's not given what is KT, you just assume it's KT lah. Because KT is just a mathematical representation. Okay. For example, here in this question, KT is actually in this module, page 55. Okay, those didn't have the book, you can refer at Telegram because Yan Hui have scanned the book. Page 55. Okay, where KT is mathematical representation of diode switching function. So KT is given. So you don't need to solve what is KT, no need. Okay. Then it is shown here, given KT is actually 1/2 plus 2 over pi cos omega ct minus cos 3 omega ct and plus so on. So this is your diode switching function, KT. Okay. If they don't give, it's just KT lah. Okay. Okay, so this is the impact of your RC value. Okay, if it's optimum, it will look like this. Okay, if it's too small, you have a lot of ripple. If it's too large, you have diagonal clipping like this. Clipping. This is clipping. Faham ke? I think you learned clipping, right? You learned clipping already. So this is the optimum lah. We cannot have too small, too many ripple. If we have too large, we will have diagonal clipping. Diagonal is like this, diagonal. Okay.
Mozzarella kan? Mozzarella tak cukup. Sambal? Sambal nak sambal merah ke?
Adriana, can you mute?
Dengan
Adriana, sambal apa tu? Okay. Adriana cakap apa? Sambal Okay. Okay, so assuming simple mathematical analysis. So this one is what has been covered by page 55. Assuming that the diode function like a switch, that its voltage VD follow. So VD equals to EC plus VM. This one is VD. It passes through the diodes, after the diodes. Okay, VD. After the diodes. VD EC, assuming that the diode function like a switch, goes on and off, we only take for a second, that is voltage VD, EC plus VMD cos omega CT. So this is your signals time with the diode switching function KT. Okay, diode switching function KT. So this is the AM, right? The full AM. Okay, this is your KT, diode switching function. And then KT is given, okay, if it's in the exam or test or final, it is given what it is, you don't need to solve. So 1.5, blah, blah, blah. And then you see VD, VPO, V point B here. Okay. After the diode switching function, what you have? You have 1 over pi EC plus VMT plus with higher frequency terms. Okay, here, before low pass filter, you have 1 over pi EC plus VMT. So how you get 1 over pi is here lah. Okay. So EC plus VMT, the same thing, EC plus VMT plus higher frequency terms. Okay. Then it passed through low pass filter where we remove the higher frequency terms. In the end, we only have EC plus VMT here. Okay, after pass through low pass filter. So we only have the lower frequency components. Okay. Then after that, at V point D, it will V point D is actually when it already passed through the DC blocker. So when it passed through DC blocker, we don't have EC. EC is 0 DC blocker. That's why you will have 1 over pi VM. You have the signal back. The information signal back 1 over pi VM. Although it is not directly equivalent to your signal, but actually you have a signal, information signal, just multiply with a factor of 1 over pi. Okay, but you still get the original signal. Okay, just with a multiplication of 1.1 over pi. Since capacitor C present direct current EC going through it. Okay, so DC blocker lah. DC blocker, we don't allow the DC current. Okay, we only allow the AC components. That's why it's DC blocker. DC blocker, where is it? Okay, AC component, we remove the DC, so we only, in the end, we have the AC component, which is here, which is this 1 over pi VMT. Okay, 1 over pi VMT, given that the diode switching function is this. So means that 1 over pi is not always 1 over pi. This is depends on what is your KT. If KT is not given, just KT lah. Okay, depends if it's given or not. If not given, then suit accordingly lah. Okay, if it's not even KT, or depends on what is this here. But at least you know, generalize that at point B, you will have this signal together with higher frequency terms. Okay, so this is pretty much what happened, okay, at each stage. So this one is also shown in the module books. Okay, so this is the original signal at the end, although it is not in the scale with your VM, but actually it's the same signal. It's just the scale with 1 over pi. Okay, this one is no problem, right? Because important thing is we're able to retrieve the signal again. Okay, so finish that. We will continue with the modulation AM DSP FC tomorrow. Okay, No, not tomorrow. This one is later. This one is the next class. The next class which is on Sunday. Okay. Tomorrow, uh, tomorrow we'll discuss the exercise. From the real past test. Please do generation and detection. Okay. We discuss it tomorrow, and I will share the Padlet. So if you do it, you learn it. If you don't do, I will not force you. Okay. This is your time where I actually can help you. Okay, you do exercise first. Okay, so thank you. See tomorrow for the tutorial. Okay, thank you.
Brother.
Okay.